Okay, so for this video, we will have more examples on rotational dynamics. So this is our first problem. We have 3-point masses lying on a flat frictionless surface are connected by massless rods. Determine the angular acceleration of the body about an axis through point mass A and out of the surface and about an axis through point mass B. So express your answers in terms of the force F, the length L, and mass M. Okay, so we have two systems here. So the first system is this whole system here, A, B, C, point masses A, B, and C, are rotating about an axis through point mass A. So the first case, na diri ato ang axis of rotation. And then the second case is our axis of rotation is through point mass B. So suppose we are looking at the top view of this system. So the axis is out of the surface. Okay, so imagine there is an axis here passing through point mass A for system A. And then for system B, there is an axis of rotation through point mass B. Okay? So such that if we are going to apply a force with magnitude F, this whole system here will rotate about those axes. Okay? So again, we have 3-point masses A, B, and C. So the distance between A and C is 2L. And then your point mass B is midway between the 2-point masses A and C. Therefore, the distance between A and B is L. And then the distance pod between B and C is also L. Okay? Now take note that your point mass A has a mass of M, point mass B has a mass of 2M, and point mass C has a mass of 3M. Okay, so again, we are given with the masses as well as the length or the distance between the point masses, the distance of the rods connecting them. Okay, so we are asked to find the angular acceleration of the body. So since we have two systems, so this is our system number 1, system number 2, then we'll have two angular accelerations to be solved. Okay, so for this, our approach is to find first the moment of inertia. So recall that moment of inertia for point masses is just equal to m times r squared. Okay, so we just have to sum up the individual moment of inertia for the 3-point masses. Okay, so for example, we have I is equal to ma r sub a squared plus m sub b r sub b squared plus m sub c r sub c squared. Okay, so let's start with system A. Okay, so let's start with system A. So again, system A is kini siya nga system, but ang iyang axis of rotation is through point A. So such that if we're going to push this through a force F, or we're going to apply a force with magnitude F, this whole system, kini siyang whole system will rotate counterclockwise about this axis. Diri okay? Alright. So, the moment of inertia of the first system. So, you have ma r sub a squared. So, your ma is m. Mass of point mass A is m. And then, this one is the length of the lever arm from the axis. So, take note that your axis of rotation is through point A. So, therefore, the distance between the axis and your point mass is 0. And then your m sub b is the mass of your point mass b. So 2m multiplied by the distance between the axis and your point mass b. So this is L. So you have L squared plus your m sub c is the mass of point mass c multiplied by r sub c. So the length gikan diri sa axis padulong sa imo point mass c is 2L. So you have 2L squared. Okay. So we simplify, this is 2ml squared plus you have 4L squared multiplied by 3m. So this is 12 ml squared. So therefore, the moment of inertia of system A is equal to 14 ml squared. Okay, now for system B, we have to use this equation also since the same naman to ang system, only that the axis of rotation is through point B na this time. Okay, so it is through point B. So naana diri atong axis. Diri na mo rotate ato ang system. Diri na siya mo rotate dapit. Okay, so if we push this with force F, so it will rotate about this axis through B. So we have I sub B is equal to, you have M sub A is M multiplied by, now since nana diri atong axis, your R sub A is kini siya nga distance which is L. So you have ML squared plus you have MB 2M, and then your R sub B is 0 this time since the axis is through B. And then we have M sub C 3M multiplied by your R sub C is this distance, so this is equivalent to L. Then you have squared. So simplifying this, we have ML squared plus 0 plus 3ML squared. So we have 4ML squared. Okay, so we have to take note of this. Alright, and then since our target variable is the angular acceleration, then we will use this equation. So we can use this equation. Or we have torque. So recall that torque is equal to I multiplied by the angular acceleration. Therefore, so we can get the angular acceleration. We can get the angular acceleration by taking the ratio of the torque and the moment of inertia. Okay. Now, note also that torque can be obtained using this equation. So we have R cross F, or if your vector R is perpendicular with the force vector, then this can just be written as R times F. Okay, so this is if R is perpendicular with F, which is the case. So let us take a look at the figure. So this is our R, the horizontal, directed horizontally, and then our F is directed vertically, so they are perpendicular with each other. So we can just write the torque as equal to R times F, the magnitude of the length of the lever arm multiplied by the magnitude of the force. So we can get two values for torque. So we have torque for system A is equal to the length of the lever arm. So this is equal to 2L multiplied by the force. So you have 2LF. And then for system B, the torque is equal to The length of the lever arm is just equal to L multiplied by F, or this is just L times F. Okay, and then after this, we will use the obtained values for the moment of inertia as well as the values of the torque to find the angular momentum. Therefore, alpha for system A, the angular acceleration for system A is equal to torque of A divided by the moment of inertia of A. So this is 2LF divided by the moment of inertia is 14 ml squared. Okay, so we can further simplify this. You have L here cancelled out, and then we have 2. The remaining in the denominator is 7. So you have 1 over 7 multiplied by F over ml. So 1 over 7 multiplied by F over ml. Or this is just equal to F over 7 ml. Okay. And then for the angular acceleration for system B, so we have tau B, or sorry, the torque of B multiplied by the moment of inertia of B. So this is equal to LF divided by 4 ml squared. So we can simplify this further. We have F over 4 ml. Okay, so this is the angular accelerations of system A and of system B.